Hello, my name is Charlotte Wittram. I am an Oxbridge Mind tutor, and today I'll be going through the fourth tutorial on the PAT Oxbridge course on mathematics, and today we'll be looking at calculus and graph sketching. So just a general lesson plan for today includes recapping common integration and differentiation techniques, the strategy for sketching graphs, and working through past paper questions. So first on to content recap. This is just a quick breakdown of what we're going to be covering today. So first we're going to have a look at integration, then differentiation, and then sketching graphs. This will all be familiar to you, you having been through Maths A-level, etc., and possibly GCSEs. You've covered some of this. And yes, now we're just going to be looking at how we can apply this to more challenging problems and how you can use integration and differentiation in graph sketching as well. So integration, we have the general equation for integration. So if you have x to the power of n and you integrate that, you'll get x to the power of n plus 1 over n. Now, you'd be expected to know how to integrate polynomials off the bat, just very, very quickly. You've got to practice these to make sure they're second nature, and when you're approaching more difficult questions, that you know how to do this extremely quickly. And another high yield topic, so topics that they love to test you on, is even and odd functions. They will sometimes just give you graphs and things and ask you to determine that, or they would expect you to look at a function, see that it's odd or even, and use the integration shortcuts shown below. So if you have a symmetric function, you know that it's going to be able to be reflected in the y-axis. And so if, as you see here, the integration from minus a to a is just the same as twice that from a to 0, or well, 0 to a. And this is just because it's symmetric. And then for an odd function, we know that if you integrate it from minus a to a, it's going to equal 0, mainly because it's axisymmetric. So if you reflect it in the y-axis, you should be able to reflect it in the x-axis to get the original function. Now we're going to move on to differentiation, and here is the product rule example we're going to have a look at. Product rule is something you should be very familiar with, which you've used all the way through A-level. So this is just a quick recap. And what you do when you have two x functions multiplied together, you differentiate the first x function and multiply it to the original second function, and then you add this to the differentiated second function multiplied with the original first part of the product, and then you end up with an differential like this. So now we're going to move on to the chain rule in differentiation. So this is just a quick recap of a rule that you've used quite a lot in your A-level mathematics. So this occurs when you have an x function inside another function. And what you do in this case, to get the total derivative of this, you take the derivative of the x function inside the other function and you multiply it with the original function differentiated. But remember to keep the original function of x within the other function. Do not change this x cubed in this case. Just keep on practicing these rules in different scenarios. As the PAT, it would be expected for you to be very fluid with using these. So make sure you have your integration and differentiation down and ready to use. So now we're going to look at graph sketching, and here are a few steps that will help you sketch graphs in any scenario. And the first step to sketching any sort of graph is identifying the intersections with the axes. So just subbing in x equals 0 or y equals 0 into your equation and finding out those intercepts, and then find out if there are any asymptotes by inspection, or trying values. So setting, for instance, x going to 0 or x going to infinity, and seeing how that function behaves over large limits. Step 2 is to differentiate your equation. And this helps you to find the turning points and differentiate again to investigate the nature of the turning points. So you know that a derivative is equal to naught at a maxima or a minima, and the derivative of that derivative will tell you whether it's a maxima or minima. So if it's a minima, the second derivative would be positive, and if it's a maxima, then the second derivative will be negative. These steps should be very on hand again, and just practice sketching many different graphs, some of which you will be completely unfamiliar to you, and I recommend doing things like sketching x to the power of x, x to the minus x, and also just practicing the normal ones like 1 over x, 1 over x squared, or logarithms as well, e to the power of something. And just remember to look at those intersections and asymptotes and differentiate it for maxima and minima. So many students find graph sketching questions intimidating and don't know where to start. And when you don't know how to start a question, just try plugging in some numbers, as it's really helpful just to experiment when tackling a difficult problem. And don't be afraid to try things out. Just draw a very clear table on your paper so that the examiner can see you're trying to gauge how this equation is will appear on a graph, and just, present to them that you are trying to figure it out and not just rushing through it and making silly mistakes. I know it's going to be hard in the exam given the amount of time that you have, but if you're really unsure, it's definitely worth just plugging in a few values using your calculator. So we're going to go on to our first pass paper question, and this is from the 2013 PAT and is question 9. This is a normal setup for PAT questions, as you can see that the first part of the question looks like you have to sketch a more simple profile than the second part of the question. And this is very normal in the PAT, as the examiners will try and set you up for a more challenging part of the question and see how you can use the techniques that we have just discussed in different scenarios. So in B, a more challenging scenario. So if we just approach part A, we are asked to sketch y is equal to the exponential of minus x. Now, this is just simply the exponential function reflected in the y-axis. So we know it's just going to look like this. And the intercept, if this is y and this is x, the intercept is going to be 0, 1. Now, just be used to sketching well-known graphs like this and be comfortable with reflecting graphs in your head and know how to apply reflections in the y-axis or the x-axis, as this will just add some more fluency to your answers and cut down time in your exam. So now we're going to sketch B, and we're going to have a look at this expression here. Now, if you remember back to step 1, we were asked to determine the coordinates of the intercepts and how the graph behaves when looking at the limits from 0 to infinity. Now, this is really useful just to practice our step 1 and step 2. So we're going to do just that. So if we see from inspection as x goes to infinity, you can see that because we've got an e to the minus values here, that all this is going to do, y is going to tend to 0. As this power, let's just call it b, as b increases, it goes to infinity, this term is just going to go to 0. And this will happen for this part and this part. So overall, y will tend to 0. So we have that asymptote there. So now we've determined that limit, we're now going to have a look at the y-intercept. So if you plug in x is equal to 0, this will give us the coordinates 0, 3e squared minus 6e. Now, we either can determine that this is going to be above the x-axis because e is more than 0, or you can just quickly plug that into your calculator just in case you're unsure. So we now know that the graph is going to intercept here at 0, 3e squared minus 6e. And we know it's going to tend to infinity along the x-axis and tend to 0 along the y-axis. So we know how it starts, how it ends, but we're not so sure what happens in here. And this is where step 2 comes into play. So you just want to differentiate this expression up here to find the turning points, and then differentiate again to investigate the nature of these turning points. So we're going to do this in the next slide. So if we just remind ourselves of the expression, it's y is 3e to 2x minus 1 minus 6e minus x minus 1. So just to simplify this, if you spot, you can take out a common term in this equation. So if we just let x equal to e to the minus x minus 1, this makes our life a whole lot easier for differentiation. So if we sub this in, y is equal to 3 x squared minus 6x, which is just equal to 3x, x minus 2. And this allows us to find the roots of this equation. So the only root is x is equal to 2. And when this is the case, x is equal to 1 minus ln 2. So now we're going to have a look at finding the turning point in this graph. So if we have a look at finding the derivative of this, we know that dy over dx is equal to minus 6x squared plus 6x, which is equal to 6x1 minus x. And all I've done is differentiate this and then substitute in my value for capital X. And this is the expression that we get. And if we set this equal to 0, because we're trying to find a maxima or minima, and we know that the derivative is going to be 0 at a maxima or minima, and then we rearrange to find x, and therefore there will be a turning point when x is equal to 1. Now, to find the nature of this maxima or minima, we then differentiate this expression again, and this would just equal to 12e minus 2 x minus 1 minus 6e minus x minus 1, which is just equivalent to 12x squared minus 6x. And then you can see from this, this is equal to 6 when x is equal to 1. So we just substitute x is equal to 1 back into here. And therefore, this is a minimum point. So we will find that by putting this all together, we know the intercept here is going to be 3e squared minus 6e. Here, well, that's y, and that's x. And then we know that there's going to be a minimum point here at 1 minus 1, because we just resubstitute our value of x into our original equation to find the coordinates. So it looks something like this, because we know that as x tends to And we know the intercept and the asymptote from step 1, and the location and the nature of this minima from step 2. So that is just a very simple and conducive answer to put this all together and show you this example using the steps. So some common pitfalls when coming across these questions is just spending too much time figuring out what the graph looks like. So just sketch graphs systematically, find axis intersections by trying numbers, and find the turning points by differentiation. And if you follow this formula, you will save a lot of time in the exam. If you've done the graph above and you're still not confident what the graph looks like, have a guess and move on. So sometimes it's hard to connect the intercept, asymptotes, and all the maxima and minima. Just guess what it looks like in between, because if the examiner sees that you've got those points and the nature of the maxima and minima, then you will get marks. Don't waste time on this. Also, it's extremely time-pressured exam, and it's important that you use your time effectively. If you follow the above steps, you will be guaranteed these partial marks, as I said. So that's the end of the 4th tutorial. I hope that was useful, and I look forward to seeing you in further tutorials on this course.